Here is a metal block. When a current is passed from point A to point B, the resistance is exactly 1 ohm. Another block of identical size and shape is placed at the end of the original block. This means that the total length is now twice as much. Consequently, the resistance is doubled, increasing from 1 ohm to 2 ohms. This shows that the resistance is directly proportional to the length. The second block is removed and is instead placed at the side of the original block. This means that the cross-sectional area is now twice as much. Consequently, the resistance is halved, decreasing from 1 ohm to 0.5 ohms. This shows that the resistance is inversely proportional to the cross-sectional area. Therefore, the overall resistance of the metal block can be said to be directly proportional to the length of the block divided by the cross-sectional area. This can also be written as R equals rho L over A, where the letter rho is a constant that represents the resistivity of the material that the block is made from.
This is Dom. Dom is a superconductor whose critical temperature is X Kelvin. When Dom becomes super cool, he has negligible resistance. Bosh.
This diagram explains how, when a material is cooled below a critical temperature, represented here by Tc, the material becomes a superconductor. This diagram demonstrates one of the benefits of superconductors. Although impractical, it shows how a long-distance power cable would need to be cooled, costing the national grid lots of money. However, it would save the energy suppliers money because they wouldn't have to produce as much energy thanks to a very big decrease in resistance from the cables. A more practical application now. This train is slow and inefficient. But this train, thanks to superconductors, is very fast and very efficient. It uses the negligible resistance of superconductors and the strength of electromagnets to float. Superconductors are used here to produce electromagnetic fields all the way along the track. The Meissner effect, which is being drawn here, is quite a quirky property of superconductors. It's where the material actively deflects electromagnetic fields. You can see here that the normal material doesn't affect the electromagnetic field, it allows it to pass straight through.
Here is an example question. Aluminium has a resistivity of 2.8 times 10 to the minus 8 ohm meters at 20 degrees Celsius and a transition temperature of 1.2 Kelvin. Part A. Calculate the resistance of a pure aluminium wire of length 4 meters and a diameter of 1 millimeter at 20 degrees Celsius. Part B. When the wire is cooled to below 1 Kelvin, what is the resistance? Explain. So for question A, we use the formula R equals rho times L divided by A, where R is resistance, rho is resistivity, L is length, and A is cross-sectional area. So we know that resistivity is 2.8 times 10 to the minus 8, length is 4 meters, and to work out the area, we need to calculate the radius. The radius is equal to 1 millimeter divided by 2. And then we need to times it by 10 to the minus 3 to convert it from millimeters to meters. Then to work out the cross-sectional area, you do 0.5 times 10 to the minus 3 all squared times by pi. When we put this into the formula, we get R equals 2.8 times 10 to the minus 8 times 4 divided by 0.5 times 10 to the minus 3 squared times pi. Which is 0.14 ohms. Question B, we need to look again at the question. In the question it tells us it has a transition temperature of 1.2 Kelvin. The question asks for when it is cooled to 1 Kelvin. Note, the material is below the transitional temperature in part B. The transition temperature tells us when a material becomes a superconductor, and we know that a superconductor has 0 resistance, or 0 ohms. So we could write the answer like this. Aluminium is a superconductor below 1.2 Kelvin, in brackets its transition temperature, and therefore will have no resistance, 0 ohms.